Welcome back to Science to Sleep By. Tonight, as you settle into your pillow and let your breathing soften, I'd like to take you on a quiet journey across the universe. Beyond the glow of city lights, past the edge of our solar system, and deeper than the reach of any spacecraft, lies a vast cosmic ocean. It is a place so wide, so dark, and so silent that even light takes millions of years to reach from one island of stars to the next. Here, in this gentle stillness, we ask a simple but profound question. Why is the universe mostly empty? This is a calm, slow-drifting exploration meant not only to teach, but to help your mind unwind, ease stress, and drift toward peaceful rest. The way millions across the US wind down each night seeking comfort, curiosity, and serenity all at once. When we look up at the night sky, especially on a quiet evening in the United States, where the stars shine with the calm, comforting familiarity, it's easy to imagine the universe as a dome sprinkled generously with lights. It feels rich, full, and infinite. But as we begin to drift into the soothing rhythm of this cosmic journey, we uncover a gentle truth. The universe, for all its brilliance, is mostly empty. The darkness between stars stretches farther than our minds were ever built to grasp, and the distances between galaxies open into silent oceans of nothingness that dwarf even the largest ideas humans have ever conceived. And as we settle deeper into this reflection, letting our breath slow and our thoughts lighten, we begin to understand that this emptiness is not cold or frightening. It is steady, vast, and deeply peaceful. Like a quiet room where the universe itself pauses to breathe. Imagine drifting upward through the sky, rising past the soft haze of the atmosphere, where the blue melts into the deep velvet of space. Down below, the world is full of movement, waves on the coasts, cars drifting along highways, wind brushing through trees. But the moment you step into the cosmic expanse, all that motion begins to fade. Out here, there is no sound. Not because the universe is hostile, but because it is open, wide, and undisturbed. Sound needs air to travel, and in the vacuum of space, there is no air at all. What remains is silence so complete that it feels almost gentle, as if the universe offers a soft blanket of stillness around everything within it. This silence has lasted for billions of years, wrapping around every star, every planet, every drifting particle of dust. It is in this silence that we begin to explore why the universe is so empty, and why that emptiness is such a natural part of its structure. As we float farther into space, the distances around us expand in ways that feel almost unreal. If Earth were a grain of sand, then the moon would be another grain placed just a few inches away. But the nearest star, Proxima Centauri, would be several miles distant, and the next star after that, several more miles. Each star is a glowing island separated by an enormous sea of darkness, a sea that stretches in every direction. And this is only the beginning of the emptiness. Our entire solar system, from the sun to the distant Oort cloud, where comets sleep for eons, is mostly nothing, a few scattered objects drifting in a region so vast that even spacecraft traveling at tens of thousands of miles per hour seem to barely move. The emptiness is not an accident, nor is it a failure of creation. It is the natural state of space itself, shaped by the laws of physics, that allowed matter to gather only in small pockets, leaving the rest as open wilderness. Even our Milky Way galaxy, with its glittering spiral arms, its hundreds of billions of stars, and its clouds of glowing gas, is mostly void. The stars are so far apart that if our sun were the size of a basketball, the nearest star would be another basketball sitting as far away as the length of a cross-country road trip. When we look at pictures of galaxies, they seem dense and bright, like swirls of light painted across a dark canvas. But if you were actually inside one of those swirls, the view would be nearly the same as it is from Earth, a few stars scattered across enormous darkness. The glowing bands we see in photographs are only visible because we zoom out far enough to compress the distances. Up close, galaxies are breathtakingly empty, built from widely spaced stars, planets, asteroids, and dust grains drifting through tremendous voids. As you sink deeper into this thought, allow the scale of this emptiness to soften your mind rather than overwhelm it. The quiet distances between stars are so large that even light, the fastest thing in the universe, needs thousands or millions of years to travel from one to another. Imagine light as a traveler walking steadily through the cosmic night. Every step takes it closer to a distant star, but the journey is so long, so unhurried, that the universe remains tranquil while it moves. There is no hurry in space, no rush or noise or interruption. Everything moves at the pace the universe allows. And in this slow movement, a deep calmness settles over everything. The emptiness exists not only around stars, but also within them. If you were to shrink down into the smallest parts of matter, into atoms themselves, you would find that they, too, are mostly empty. The nucleus is tiny, surrounded by vast space where electrons drift in blurred clouds. The structure of matter mirrors the structure of the cosmos, tiny pockets of something held within a sea of nothing. It is a pattern repeated from the smallest scales to the largest, reminding us that emptiness is not the absence of meaning, but a fundamental part of everything that exists. When we look at the night sky, we are not gazing into a universe overflowing with stars, but into one that uses emptiness as its canvas. The stars shine because the darkness around them allows their light to travel freely. Galaxies form because space gives matter the room it needs to gather and spiral. And planets like Earth exist because, in the vast calm of the cosmos, small regions of matter can cool, settle, and eventually support life. Emptiness is the stage on which creation unfolds, offering stillness where structure can form and time can pass gently. To understand why the universe is mostly empty, we must drift back to a moment so ancient and so distant that it sits beyond the reach of memory, beyond the reach of galaxies, beyond even the stars themselves. Picture yourself resting comfortably, your breathing soft and steady, as we gently step into a story that began nearly 14 billion years ago. It's a story that doesn't begin with stars or planets or swirling galaxies, but with the sudden expansion of space itself, a moment called the Big Bang. Not an explosion in the way fireworks burst across a summer sky, but a profound stretching of the cosmic fabric, where space blossomed outward faster than any object within it could keep up. This moment is the quiet origin of the emptiness that surrounds us today. In the very beginning, the universe was incomprehensibly small, compressed into a state of incredible density and heat. Everything, energy, matter, time, was packed together as tightly as possible. Imagine holding all the stars, all the planets, every grain of dust, every photon of light, all of it pressed into a space no larger than a speck. It was a universe waiting for release, a universe where emptiness did not yet exist. In that compressed state, the concept of distance had no meaning, because there was nowhere to travel. Yet within that tiny spark of existence lay the blueprint for everything that would come: gravity, light, atoms, galaxies, and the vast silent expanses that would cradle them. And then, in less than a blink, space began to expand. Not slowly, not gently at first, but with a speed and force far beyond anything we can witness in the present universe. The best way to picture it is not through an explosion hurling objects outward, but through space itself, growing, swelling, stretching in every direction at once. Where once there had been no separation between points, now there was distance. Where once everything was crowded together, now there was room. The fabric of the universe puffed outward so rapidly that matter didn't have time to distribute itself evenly across this new space that had formed. Instead, matter was left behind in tiny clumps. And the rapidly expanding voids between those clumps soon grew into the enormous cosmic emptiness we see today. This early expansion phase, known as cosmic inflation, happened so quickly and so quietly that if you were somehow floating there calm, weightless, watching the universe open around you, you wouldn't feel a breeze or hear a sound. Inflation doesn't push matter like wind pushing leaves. It simply stretches the space between things, increasing the distance without disturbing the serenity of the cosmos. Imagine the markings on a balloon as you gently blow it up. The dots move apart, not because they are crawling away, but because the surface beneath them expands. In the same way, the primordial universe expanded beneath the matter it held, pulling everything farther apart without motion in the traditional sense. As the universe continued to stretch, temperatures dropped. The extreme heat of the early moments slowly faded, and the thick, opaque fog of plasma-charged particles and light tangled together began to cool. This cooling allowed particles to slow down, to combine, to begin forming the first building blocks of atoms. Hydrogen and helium were born in this gentle cooling phase, the simplest elements that would eventually fuel stars and galaxies. But even as matter formed, the expansion continued, creating more and more space around it. The universe had grown so vast, so quickly, that these newly formed particles were scattered thinly across cosmic distances. There was simply too much room, and not enough matter to fill it. Imagine standing in a vast field stretching farther than the horizon, holding only a handful of grains of sand. No matter how you scatter them, they will never cover the ground. That's what happened in the early universe. Matter existed, but not enough to fill the immense volume that inflation had created. And so, the universe grew into a place where emptiness wasn't just common, it was dominant. The tiny clumps of matter that did exist were like small seeds drifting in an endless ocean of space, slowly gathering together under the influence of gravity. These seeds would eventually form stars, galaxies, and every structure we know today. But the vastness of space, the deep oceans of nothingness between them, were already established from the very beginning. As we sink deeper into this understanding, let your mind drift back to those early moments when the universe was still young. Space was dark, filled not with stars or planets, but with potential. There was no sound, no light traveling freely, no galaxies carving their graceful spirals through the cosmic night. Just a quiet, expanding fabric, gradually cooling, gradually shaping the future. The silence of that early universe is the same silence that fills the cosmos today. It is a silence born not of emptiness alone, but of a universe expanding so quickly that light itself struggled to keep up. As billions of years passed, gravity began to pull matter together, forming stars that flickered into existence and galaxies that spun with elegant balance. But even as these structures grew, the empty space between them remained dominant. The expansion that began in the first fractions of a second never truly ended. It continued throughout cosmic history, stretching the universe further and further apart. Today, galaxies drift away from each other as space itself grows, carried along not by momentum, but by the ongoing expansion that began at the dawn of time. And with every passing moment, the universe becomes a little more spacious, a little more quiet, a little more empty. The emptiness of the universe, then, is not an accident or an oversight. It is the natural consequence of a beginning where space expanded far more quickly than matter could gather. It is the echo of a moment so powerful and so silent that it still shapes the cosmos today. And as we float through this understanding, we find a gentle peace in knowing that the universe was born not into fullness, but into openness, giving everything room to form, to grow, and to drift through the quiet night of space. As we continue drifting through the quiet expanse of the cosmos, letting the calm of the night ease tension from your thoughts, we come to one of the most delicate and softly powerful forces in the universe: gravity. It shapes the stars that shine above American suburbs and big cities alike. It keeps planets in orbit around their suns, and it gathers galaxies into swirling patterns that span millions of light years. Yet despite its influence, gravity is a surprisingly gentle force. It works slowly, patiently, and quietly, never rushing, never demanding, never forcing. And this quiet nature plays a major role in answering why the universe is mostly empty. To understand the emptiness that surrounds us, we must understand the way gravity tries to bring things together and the ways in which it cannot. Picture yourself floating in space, weightless, your body suspended in a stillness so complete it feels like time itself is resting beside you. Out here, nothing tugs sharply or pushes abruptly. Gravity's pull is soft, almost unnoticeable unless you are incredibly close to something massive. If you drift near a planet like Earth, gravity becomes strong enough to guide your fall. But just a little farther away, the strength of that pull fades quickly. By the time you move even a tiny fraction of the distance to the next planet or star, Earth's gravitational influence becomes virtually non-existent. Gravity weakens with distance, far more dramatically than most people imagine. And that weakening is one of the key reasons why matter stays so far apart across the universe. Every object with mass planets, stars, galaxies, even you creates a gravitational field that extends outward forever. But the farther away you get, the softer the pull becomes. If you double your distance from something, its gravity becomes 4 times weaker. If you triple your distance, gravity becomes 9 times weaker. This rapid decrease means that even though stars have enormous mass, their gravitational reach is extremely limited across the scale of the universe. Stars cannot pull in other stars that are light years away. Galaxies cannot easily capture distant galaxies. Matter simply cannot gather fast enough or strongly enough to fill the vastness of space that formed after the Big Bang. Gravity tries to shape the universe, but its influence fades so quickly that enormous regions are left untouched, drifting in the peaceful emptiness between cosmic structures. In the early universe, after the furious expansion of cosmic inflation slowed, gravity began its slow and steady work. Tiny fluctuations, slightly denser regions of hydrogen and helium started to pull in more gas, forming the seeds of galaxies and eventually stars. But the vast majority of space had no such dense regions. Most of the universe remained too smooth, too evenly spread out, for gravity to corral matter together. Instead of pulling everything into immense clusters, gravity could only gather matter where matter already had a slight head start. These small pockets collapsed into galaxies, while the enormous stretches of in-between space remained uncollected and empty. Imagine spreading a handful of fine sand across a football field. Wherever a few grains land close together, wind or water can gather them into tiny piles. But the rest of the field stays bare. Gravity works in much the same way. It collects only what is close enough to influence, and everything else remains scattered, peacefully drifting in the openness of space. The result is a universe filled with islands of matter floating in a sea of nothingness, beautiful galaxies surrounded by vast expanses so empty that a single cubic meter of space may contain only a few atoms, or none at all. As we let this idea settle gently in the mind, consider how long gravity takes to shape the cosmos. Stars form over millions of years, galaxies over billions. Gravity is patient, and the universe is old. But even with all that time, gravity is simply not strong enough across cosmic distances to gather all the scattered matter into a dense universe. Space expands faster than gravity can keep up, pulling galaxies away from each other while gravity tries to hold them together. In some regions, gravity wins, knitting galaxies into clusters and clusters into superclusters. But between these great networks of structure, space stretches wide and empty, leaving behind enormous voids that gravity cannot bridge. Even inside galaxies, emptiness dominates. Stars appear close when viewed from afar, but the distances between them are astonishing. If our sun were the size of a large orange, the nearest star would be another orange sitting hundreds of miles away. Gravity keeps stars loosely bound within their galaxy, but it does not pull them tightly together. If it did, stars would crash into one another, and galaxies would collapse into dense balls of fire. Instead, gravity's gentle nature ensures that stars orbit peacefully with enormous gaps between them. This balance allows galaxies to remain stable and graceful, but also ensures that they remain mostly empty. As you drift deeper into this understanding, think about how gravity shapes your everyday life. It keeps your feet on the ground, holds the oceans in their basins, and guides the moon around Earth. It feels strong because you are close to a massive object. But in truth, gravity is the weakest of the 4 fundamental forces of nature. It is far weaker than the forces that hold atoms together. It is even weaker than the force of a refrigerator magnet lifting a paper clip against the pull of an entire planet. Gravity only appears powerful when enormous amounts of mass are involved. Without vast collections of matter, gravity is nearly silent, almost imperceptible. And across the tremendous distances of space, Even enormous collections of matter lose their grip. So the universe's emptiness is not due to a lack of matter, but to the balance of forces and scales. Gravity can gather matter only in certain places, and only slowly, while the fabric of the universe continues to expand. The result is a cosmos where matter forms delicate structures woven through a background of almost perfect emptiness. The stars shine brightly, not because space is full, but because space is open enough to let their light travel freely. Galaxies exist not because matter dominates, but because gravity gently brings together what little mass exists within reach, and the quiet spaces between them stretch endlessly, calm and undisturbed, shaped by the limits of gravity's soft embrace. As we continue drifting deeper into the quiet and contemplative stillness of this cosmic journey, imagine yourself floating weightlessly, the way one might feel in a dream. The vast emptiness of space surrounds you, gentle, silent, and open, and yet the same emptiness exists in a place far closer, far more intimate, far more familiar. It exists within you. It exists in every object you've ever touched, every breath you've ever taken, every thought that has ever moved across your mind. At the heart of everything in the universe, from the largest galaxy to the smallest grain of dust, lies a profound truth. Matter itself is mostly empty space. And when we explore the structure of atoms, the tiny building blocks of all existence, we begin to understand that emptiness is not simply around us, but woven into the very foundation of reality. Picture an atom, not the simple diagram from a school textbook, with neat, circular orbits and tidy labels, but a quiet, drifting structure almost too small to imagine. If we were to enlarge a single atom until the nucleus, the dense center, became the size of a marble, then the nearest electron would be floating hundreds of feet away. All the space between them, all that volume, all that room, would be empty. Not empty in the sense of quiet air or soft water, but empty in the truest sense. No particles, no light, no matter at all. It is pure space, a calm void inside the heart of everything that exists. This emptiness on the atomic scale mirrors the emptiness we see in the cosmos. Just as stars are separated by vast gulfs, the components of an atom are separated by distances proportionally in more extreme. The nucleus is incredibly small, unimaginably dense, holding nearly the entire mass of the atom in a space so tiny that it almost escapes comprehension. Surrounding it is a cloud of electrons, not orbiting in neat circles, but existing as wave-like probabilities, soft, uncertain blurs of presence that shift and spread in patterns defined by quantum rules rather than classical motion. Between the nucleus and the electron stretches an expanse so empty that if atoms were scaled up to the size of cities, the areas inside them would feel like abandoned landscapes, with only a single point of matter at the center and faint, drifting traces of presence at the edges. Letting this idea settle gently in the mind, we begin to see how everything we perceive as solid wood, metal, water, even our own skin, is composed of structures that are mostly empty. When you press your hand against a table, it feels firm, resistant, unyielding. But what you're feeling is not atoms touching atoms. They never actually touch. Instead, you feel the electromagnetic forces of the electrons in your hand repelling the electrons in the table. It is fields interacting, not matter pressing against matter. At the atomic level, nothing ever truly comes into contact. Instead, forces create the illusion of solidity, while underneath it all is an ocean of space. This emptiness does not make matter weak or insubstantial. Quite the opposite. The structure of atoms, the separation between the tiny nucleus and the faint electron cloud, is what gives matter its stability. Electrons move, shift, and settle into patterns defined by energy levels and quantum balances. Their arrangement determines the properties of elements, the behavior of molecules, and the richness of chemical reactions. All of this complexity, all of this richness, emerges from a structure that is overwhelmingly empty. Emptiness is not a flaw in the design of atoms. It is the very framework that allows structure and complexity to exist. Imagine the early universe again. When the first atoms formed as space cooled, hydrogen atoms drifted through the emptiness, light and simple, composed mostly of their own internal emptiness. Their tiny nuclei, single protons, floated within vast spaces defined by their lone electrons. These atoms, each a small pocket of nearly pure emptiness, assembled into clouds, which gravity slowly gathered into stars. And inside those stars, atoms fused to create the heavier elements carbon, oxygen, nitrogen, iron, all of which shared the same basic structure: tiny, dense centers surrounded by enormous regions of empty space. These atoms eventually formed planets. They formed oceans. They formed life. They formed you. As you rest in the calm of this reflection, consider how strange and beautiful it is that everything you experience as solid, warm, or comforting is built from emptiness arranged into patterns. The floor beneath your feet when you wake up in the morning, the keys of a piano played softly in the evening, the smooth surface of a cup held between gentle hands, all are formed by atoms whose insides are mostly void. The solidity comes not from matter filling space, but from the rules that govern how electrons behave, how they resist being forced too close, how they settle into configurations that define the shape, texture, and strength of the world. This atomic emptiness also plays a deeper, more subtle role in the universe. It allows light to travel. If atoms were filled solid all the way through, light would bounce off everything instantly, unable to pass. Instead, because atoms contain so much empty space, light can weave between them, bending, scattering, or passing through, depending on how electrons interact with it. The transparency of air, the clarity of water, even the soft glow of starlight as it drifts across millions of light years, these are all possible because atoms are mostly empty. The emptiness between electrons and nuclei is what lets the universe shine, and just as the emptiness inside atoms gives rise to the properties of matter, the emptiness between atoms gives rise to the structure of objects. In a cube of solid metal, atoms are arranged in repeating patterns, yet each one is still overwhelmingly empty internally. The structure of a diamond, known for its incredible hardness, relies on the way carbon atoms bond, not on the atoms being full. The seeming strength of such objects is a testament to the balance between empty space and the forces that govern it. When we compare the structure of an atom with the structure of the universe, a beautiful symmetry appears. Small pockets of mass exist within vast regions of emptiness. The nucleus mirrors a star. Electrons mirror planets or clouds. The space between mirrors the voids of the cosmos. The universe is not an anomaly in being mostly empty. It is reflecting the same pattern found in the building blocks of matter. So as you rest in this quiet exploration, let the understanding settle gently that emptiness is not something to be feared or dismissed. It is a fundamental part of space, of matter, of reality. It is the stage on which energy dances, where forces interact, where particles drift, and where existence finds room to form, grow, and evolve. The universe is mostly empty, not only on the cosmic scale, but on the microscopic one. And it is precisely this emptiness that makes everything possible as we continue drifting through this calm, cosmic journey. Allow your mind to soften once more, as if you're sinking slowly into a warm, weightless ocean. The stars feel distant, the galaxies like faint brushstrokes painted across a canvas that stretches endlessly. And in this stillness, in this quiet drifting, we arrive at one of the most mysterious forces in all of existence, something invisible, intangible, and yet profoundly powerful. It is a force that shapes the emptiness of the universe, stretches the fabric of space itself, and gently, relentlessly increases the distance between galaxies. This force is known as dark energy, and it helps explain why the universe is not only empty, but becoming emptier with each passing moment. To begin understanding dark energy, imagine floating in the vastness of space, far from planets, stars, or clusters. There is no sound, no wind, no sensation of movement. You are suspended in a cosmic silence so deep that even time seems to slow. If you could look around, you would see galaxies drifting in every direction, each one made of billions of stars. Yet these galaxies are not simply drifting by accident. The space between them is stretching, expanding like a slow, steady breath. This expansion began in the earliest moments after the Big Bang, but scientists once believed that gravity would gradually slow it down. After all, gravity pulls matter together. It binds stars into galaxies, galaxies into clusters, and clusters into vast superclusters. It is natural to assume that gravity would slow the expansion of the universe, perhaps even stop it someday. But something far stranger is happening. In 1998, astronomers observing distant dying stars supernova made an astonishing discovery. Instead of slowing down, the universe's expansion was speeding up. Galaxies weren't just drifting apart, they were accelerating away from one another. The fabric of the universe wasn't coasting. It was stretching faster and faster over time. This was a shock to science. A whisper from the universe, revealing a truth even more mysterious than gravity. Something was pushing space to expand. Gently, but insistently, everywhere, and all at once. And that something became known as dark energy. Dark energy is not a substance you can touch. It is not a field you can see. It does not glow. It does not interact with light, and yet it influences the very shape and destiny of the cosmos. The best way to imagine it is to think of space itself having a kind of built-in tension, a quiet pressure that encourages it to stretch. Not the way rubber stretches when pulled, but the way yeast expands dough from within. The expansion is not coming from the edges. It comes from every point in space at once, pushing galaxies apart as the fabric beneath them grows. This gentle but relentless stretching makes the universe larger with every passing second. And the more space expands, the more dark energy seems to influence it, because dark energy does not thin out as the universe grows. Matter becomes more diluted as space expands, but dark energy remains constant. So the larger the universe becomes, the more dominant this mysterious force becomes, creating an ever-increasing emptiness between galaxies. Imagine watching two distant galaxies drifting apart like lanterns floating on a dark lake. At first, they move slowly, their light barely shifting. But as the water beneath them expands, the distance grows faster and faster, until eventually, they move away more quickly than light can reach across the gap. They do not speed through space. Rather, space itself stretches between them. This is what dark energy does. It increases the distance between galaxies, not through motion, but through expansion. And in doing so, it creates a universe where emptiness is not only common, but inevitable. As you let this idea settle, imagine the night sky over a quiet American town. Asterisms soft and familiar. The Milky Way faintly glowing across the darkness. If humanity existed far into the future, millions or billions of years from now, the night sky might look very different. Distant galaxies, now visible through telescopes as delicate spirals and glowing smudges, would eventually drift beyond visibility entirely. They would slip away, not because they moved too fast, but because the space between would stretch until their light could never reach us. The cosmic web of galaxies would pull apart strand by strand, leaving each group isolated in its own widening bubble of space. The universe would grow lonelier, quieter, more spacious. Dark energy does not work quickly or violently. Its influence is subtle, almost tranquil. It does not disrupt the stars within a galaxy, nor does it pull planets from their orbits. Gravity remains dominant in small regions, binding solar systems and galaxies together. But on the largest scales across hundreds of millions or billions of light-years, dark energy becomes the quiet conductor guiding the universe's expansion. It is the reason galaxies are faint islands scattered across an ocean so immense it defies imagination. It is the reason cosmic voids, the empty spaces between galaxy clusters, grow larger over time. And it is the reason why matter is stretched thin across a universe that becomes more spacious with every moment. Consider how tranquil this process truly is. There is no tearing, no sound, no force that you would feel if you floated alone in the cosmic dark. The expansion of space is silent. It is smooth. It is gentle. Galaxies drift apart like slowly separating clouds, carried by a current that works everywhere and nowhere at once. The emptiness between them softens and expands like a deep, cosmic breath. We do not know exactly what dark energy is. It might be a property of space itself, or a field that permeates the universe. It might be something we cannot yet imagine, waiting for future generations to understand. But we do know this: dark energy shapes the universe's vast emptiness. It ensures that matter will never fill all of space. It guarantees that galaxies will never gather into one place. It makes sure that the universe will always feel peaceful, open, and incredibly, profoundly spacious. And so, as we drift through this reflection, we come to see that the universe is mostly empty, not because matter is scarce, but because dark energy stretches the cosmic fabric faster than matter can gather. It is a gentle force, almost soothing in its constancy, guiding the universe into an infinite calm where galaxies float apart like quiet lanterns fading into the night sky. As we float deeper into this quiet exploration of the cosmos, imagine the universe not as a scattered collection of stars tossed randomly into darkness, but as something far more structured, far more elegant, and surprisingly delicate. When astronomers look at the universe on the largest possible scales, beyond individual galaxies, beyond clusters, even beyond superclusters, they see patterns. They see threads, filaments, bridges, and intersections. They see shapes that resemble a vast, three-dimensional web stretching across billions of light years. And between those glowing strands of matter lie enormous regions of emptiness, cosmic voids, so vast, so open, and so silent that they make even the distances between stars feel small. These voids help explain why the universe is mostly empty, and why matter is arranged in such a gentle and intricate cosmic tapestry. Picture this cosmic web. Imagine that you are drifting outside of space and time, looking down at the universe from a vantage point no human could ever reach. At this unimaginable scale, galaxies stop looking like individual islands. Instead, they gather into clumps and strings, connected like beads on invisible threads. These threads are the filaments of the cosmic web, long, thin structures where matter has accumulated over billions of years under the influence of gravity. At the points where several filaments meet, the universe forms clusters and superclusters, regions rich with galaxies and dark matter. The filaments themselves stretch across space like luminous bridges, connecting one cluster to another. But the most astonishing feature of this cosmic landscape is not the structure. It is the emptiness around it. Between the filaments lie enormous spherical or irregular regions known as cosmic voids. These voids can span tens, hundreds, or even thousands of millions of light years. In many of them, there are almost no galaxies at all, sometimes just a handful, sometimes none. They are the most empty places in the universe, great cosmic chambers where matter never gathered, where stars never ignited, where galaxies never formed. These regions are so vast that light takes hundreds of millions of years to cross them, drifting through silence more profound than anything we could ever experience on Earth. Truly feel the scale of a cosmic void. Imagine standing at one edge and looking across. If a beam of light set off from one side, moving at the ultimate speed limit of the universe, it would not reach the opposite side for longer than the human species has existed. And during that entire journey, the light might encounter only a few atoms of hydrogen scattered through space. Not stars, not planets, not galaxies, just the faintest whisper of matter, drifting through an expanse that borders on pure nothingness. These voids formed because of the early fluctuations in the density of matter after the Big Bang. Some regions began with slightly more matter than others, barely a fraction of a percent more. Gravity drew those slightly denser regions together, amplifying the growth of what would eventually become galaxies and clusters. Meanwhile, regions that began with slightly less matter were left behind. Gravity did not have enough strength there to gather the thinly scattered particles into anything substantial. As billions of years passed, the denser regions grew denser, and the emptier regions grew emptier. It was as if the universe gently sorted itself, forming a cosmic pattern where matter flowed into filaments like water flowing into valleys, leaving vast deserts of emptiness between them. Let this image float softly through your imagination. a universe where matter behaves like a slow-moving tide, gathering in some places while leaving others untouched. The cosmic web is not rigid. It shifts, evolves, and changes shape over billions of years. Filaments slowly stretch as the universe expands. Clusters of galaxies drift apart. In the voids, these enormous hollows of space grow larger, widening as dark energy pushes galaxies away from one another. Over time, the emptiness becomes even more dominant, even more pronounced, yet there is a subtle beauty in these voids. They are not merely leftover spaces that nature forgot to fill. They play an essential role in shaping the universe. The cosmic web forms because voids and filaments interact. As voids expand, they push matter toward the denser filaments, reinforcing the pattern. Imagine bubbles in a pot of boiling water. As each bubble grows, it compresses the regions between bubbles into thin walls. The cosmic web forms in a similar way, though on a scale so large that no analogy truly captures it. The universe becomes a foam-like structure, where empty regions expand and matter settles into the boundaries between them. This process, stretching across billions of years, has sculpted the universe into something astonishingly sparse. If you were to pick a random point in the universe anywhere, you would almost certainly find yourself in a void, far from galaxies, far from stars, far from anything familiar. The chance of finding yourself near a galaxy, alone inside one, is extremely small. Matter is concentrated in a tiny fraction of the universe's total volume. The rest is openness, quiet space stretching endlessly in every direction. Even the Milky Way, our home galaxy, exists along one of the filaments in this cosmic web. Surrounding our filament is the local void, a vast and eerily quiet region where galaxies are scarce. Our own galaxy is gently sliding away from that void, pulled by the gravitational tug of nearby clusters and filaments. It is as if the void is gently exhaling, expanding, giving space to the structures around it. When astronomers look into these voids, they see something remarkable. Galaxies at the edges of voids move faster than those deep inside filaments. This is because voids expand more rapidly than dense regions. They are like balloons within the fabric of the universe, stretching large and smooth, pushing against the cosmic structures that surround them. And as the universe continues to expand under the influence of dark energy, these voids will only grow larger, deeper, and emptier. As you drift through this concept, imagine traveling into a void. The stars behind you would gradually fade, the galaxies becoming fewer and farther between, until eventually you found yourself surrounded by nothing but distant glimmers of light. You would be adrift in a darkness so complete that even the familiar glow of the Milky Way would be a faint memory. Yet this emptiness would feel peaceful, almost soothing, a quiet chamber carved into the universe, shaped by billions of years of cosmic evolution. The cosmic web and its vast voids together create a universe that is exquisitely structured, yet overwhelmingly empty. This emptiness is not accidental. It is an essential feature of how the universe grows and evolves, how galaxies form, how matter gathers, and how the cosmos expands into the deep, serene quiet of its own future. In the grand design of the universe, the glowing filaments are important, but so are the voids. The emptiness gives structure its meaning. The darkness gives light its brilliance. The silence gives cosmic evolution its room to unfold. And through this intricate interplay of matter and void, the universe reveals a truth that stretches from the atomic scale to the vastest reaches of space. Emptiness is not a gap in the universe's design, but the canvas upon which all existence is drawn. As we drift deeper into the quiet mystery of why the universe is mostly empty, it becomes impossible to ignore the presence of a force so subtle and yet so powerful that it shapes the fate of the cosmos itself. Particles can become entangled, meaning their properties are linked across vast distances, so that the state of one instantly affects the other, even if they are light years apart. Albert Einstein famously called this spooky action at a distance, unable to accept that reality could be so non-local. Yet, experiment after experiment has proven it to be true. What does this mean for the stability of the universe? It means that the very fabric of existence is constantly in motion, constantly flickering between being and nothingness. Even in what we call empty space, particles are appearing and disappearing in a restless quantum dance. This background activity is known as vacuum fluctuation. The vacuum is not truly empty. It is a storm of creation and annihilation at unimaginable speeds. These fluctuations can momentarily give rise to virtual particles that borrow energy from nothing, exist for a fleeting instant, and then vanish again. In most cases, their effects are tiny and transient, but some physicists suggest that under the right conditions, these fluctuations could trigger enormous consequences, even the collapse or transformation of the universe itself. Among the most haunting possibilities is the concept of vacuum decay. According to some interpretations of quantum field theory, the vacuum we live in, the underlying energy state of the universe, might not be the true, most stable vacuum. It could be a false vacuum, metastable state that only appears stable, but is actually temporary. If a quantum fluctuation were to nudge a small region of space into a lower energy state, it could create a bubble of true vacuum. That bubble would expand at the speed of light, destroying everything in its path, not violently, but quietly rewriting the laws of physics as it went. There would be no warning, no signal, no time to react. The entire structure of matter, energy, and spacetime would dissolve into something entirely new. It sounds like science fiction, but it's a real theoretical possibility. The fact that the universe still exists may mean that the false vacuum, if it exists, is incredibly stable, or it may simply mean that the quantum dice haven't rolled against us yet. Either way, this idea underscores just how delicate the universe's foundations are. Everything we know and depend on the constants of nature, the strength of forces, the very concept of time could hinge on the fragile equilibrium of a quantum field. The cosmos could be balanced on a razor's edge between existence and oblivion, and we would never know it. Even more astonishing is how this quantum instability gives rise to structure and meaning on a cosmic scale. The same fluctuations that make reality uncertain also seeded the galaxies themselves. In the early moments after the Big Bang, tiny quantum variations in the density of matter were stretched by cosmic inflation into vast ripples that became the large-scale structure of the universe. The galaxies, stars, and planets, everything we see today, are the amplified shadows of quantum noise from the birth of time. The universe's complexity and beauty emerged not in spite of quantum chaos, but because of it. What appears to be a weakness at the smallest scales becomes the very engine of creation at the largest. Still, the quantum world continues to challenge our deepest assumptions about reality. The boundary between the microscopic and the macroscopic is blurry. Experiments have shown that quantum effects can influence systems far larger than individual atoms. Some theories even suggest that spacetime itself might be quantized, that at the smallest scales, space and time come in discrete packets, rather than continuous flows. If this is true, then the smooth fabric of reality is an illusion, a kind of cosmic simulation built from countless tiny grains of information. The universe may not be infinitely divisible, but pixelated, like a holographic image projected from deeper dimensions of reality. At the quantum level, even causality, the idea that causes precede effects, begins to lose meaning. Events can appear to influence one another in ways that seem to transcend time. In some interpretations of quantum mechanics, the future can affect the past. Others propose that every possible outcome of every quantum event actually happens, spawning an infinite number of parallel universes where each version of reality plays out. If so, then our universe may be only one of countless branches, each diverging from the same quantum uncertainty that governs the smallest particles. The deeper we look, the less certain everything becomes. The quantum world reveals that existence is not built on solid ground, but on probability, fluctuation, and constant change. The universe, for all its vastness and grandeur, depends on this invisible chaos and underlying randomness that gives birth to order and then threatens to erase it. What we call reality is merely the temporary pattern that emerges from the dance of uncertainty, a fragile tapestry woven from the trembling threads of possibility. The universe, at its most fundamental level, is not made of matter or light, but of space and time themselves, a vast, flexible fabric that stretches, bends, and curves under the influence of energy and mass. Einstein's general theory of relativity revealed that gravity is not a force pulling objects together, but rather the warping of this cosmic fabric. Stars and planets move not because they are tugged by invisible strings, but because they follow the curves and dips that their own presence creates in the geometry of spacetime. It's an elegant idea, simple yet profound, that replaced Newton's static universe with one that moves, breathes, and responds. Yet, even this beautiful model hides a darker truth. The fabric of spacetime may not be perfect. It may have cracks, tears, and weaknesses that we are only beginning to glimpse. To imagine spacetime, think of a trampoline stretched tight under tension. When you place a heavy ball in the center, the fabric dips, and smaller objects roll toward it, not because they're pulled, but because they follow the slope created by that indentation. This is how gravity works. The sun bends the space around it, and Earth follows the curved path created by that distortion. But what happens if you stretch the fabric too far, or push too much weight into it? The fabric can tear, twist, or ripple, sending waves outward. These ripples are real. In 2015, scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the first time. Ripples in spacetime caused by the collision of two massive black holes. The discovery confirmed Einstein's century-old prediction and proved that the universe itself can shudder. That spacetime is not an abstract stage, but a living, dynamic entity capable of trembling under immense stress. But if spacetime can ripple, could it also rupture? Could there be places where its smooth continuity breaks down? Physicists suspect that at the smallest possible scales, near the so-called Planck length, about 1035 meters, spacetime may no longer be smooth at all. Instead, it might froth and fluctuate like boiling water, forming a quantum foam. In this foam, the geometry of the universe is constantly shifting, with tiny wormholes forming and vanishing in an instant, particles of spacetime bubbling into and out of existence. At such scales, the classical picture of spacetime as a continuous sheet collapses into chaos. Gravity and quantum mechanics, the two pillars of modern physics, no longer agree on what happens there. The equations of relativity describe spacetime as a smooth continuum, while quantum mechanics insists that nothing can be perfectly smooth or certain. The result is a fundamental tension, a tear in the unity of physics itself. Nowhere does this tension become more evident than in the heart of a black hole. A black hole is the ultimate stress point in the fabric of spacetime, where gravity grows so intense that even light cannot escape. According to Einstein's equations, matter inside a black hole collapses into a point of infinite density, known as a singularity. At that point, spacetime curves infinitely, and all known laws of physics break down. The singularity represents a literal tear in the fabric of the universe, a place where spacetime ceases to have meaning. Some theories suggest that these singularities are not just points of destruction, but gateways to new regions of space and time. Others believe they mark the limits of our understanding, boundaries beyond which the universe hides its most intimate secrets. Even on larger scales, spacetime shows signs of strain. The discovery of cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang, implies that spacetime can stretch faster than the speed of light. During this inflationary period, quantum fluctuations were stretched to cosmic scales, seeding the structure of the universe. But this rapid expansion may have left scars, defects in the geometry of spacetime itself. Some cosmologists have proposed that the universe could contain cosmic strings, ultra-thin filaments of immense energy left over from the early universe. These strings, if they exist, would be cracks in spacetime, remnants of its violent birth. Though invisible, they would bend light and warp space, creating gravitational lensing effects that astronomers could, in theory, detect. So far, none have been observed, but the search continues. Another potential flaw lies in the universe's expansion itself. Observations show that different methods of measuring the rate of cosmic expansion, the Hubble constant, yield conflicting results. The difference is small but persistent, and it cannot be explained by experimental error alone. Some scientists believe this discrepancy could be a sign that our understanding of spacetime is incomplete. Perhaps spacetime behaves differently on cosmic scales than it does locally. Perhaps the universe's geometry is subtly twisted, or the laws of gravity themselves evolve over time. If true, then what we call the fabric of spacetime may not be as uniform or unchanging as once believed. It could be stretching unevenly, its threads pulled tighter in some places and looser in others, as if the universe were quietly straining under the weight of its own existence. Gravitational waves, black holes, cosmic strings, and quantum foam all point toward a deeper truth. The universe is flexible, but not invincible. Like any structure under constant pressure, it endures stress, tension, and fatigue. Over billions of years, galaxies collide, dark energy accelerates expansion, and black holes consume matter, all of it feeding energy back into the very fabric of spacetime. These processes may create conditions where spacetime itself could fracture. If such fractures exist, they could be the birthplaces of new universes, bubbles of spacetime budding off from our own, each with its own laws of physics. Some theories of cosmology suggest that our universe may have emerged from such a rupture, born from the decay of another. In this view, spacetime's weakness is also its creative power. Every tear becomes a seed for new existence. But even creation comes with cost. If the fabric of spacetime can tear, then it can also unravel. The accelerating expansion of the universe, driven by dark energy, stretches spacetime more and more each day. Over unimaginable timescales, this could lead to a future where the distances between galaxies grow infinite, where even the atoms that compose matter are torn apart by expansion, a cosmic event known as the Big Rip. In that scenario, spacetime itself would lose cohesion, disintegrating into chaos. The laws of physics would cease to function, and reality, as we know it, would dissolve back into the quantum foam from which it emerged. The notion that the universe's foundation can deform, ripple, and even rupture challenges the very idea of permanence. Space and time, which seem so stable and absolute, are revealed to be elastic and uncertain. Every gravitational wave that passes through us, every black hole that forms, every expansion of a galaxy cluster is a reminder that the universe's structure is not unbreakable. As we reach the end of this slow, quiet journey through the vastness of the cosmos, allow yourself to drift for a moment in the stillness that the universe has carried since its earliest moments. From the very beginning, the universe has been a place shaped not merely by the stars that shine within it, but by the immense oceans of emptiness that stretch between those islands of light. That emptiness is not a flaw in the universe's design, nor is it a void waiting to be filled. It is the foundation upon which everything else rests, the silent stage on which galaxies ignite, stars are born, planets take shape, and life eventually emerges. When we first explored why the universe is mostly empty, we discovered that emptiness has been present from the very first. Fractions of a second after the Big Bang, tiny fluctuations in the early fabric of space set the stage for matter to gather. In some places, while leaving other regions nearly untouched, those untouched regions expanded into the vast cosmic voids we see today, shaping the great web of galaxies that stretches across billions of light-years. As we drifted deeper, we found that stars and galaxies form only in rare pockets of space. The universe is so vast, and matter so thinly spread, that stars like our sun are small flickers in a dark and boundless expanse. Between the stars, emptiness spans light years. Between the galaxies, it spans millions. And across the cosmic web, silent voids grow wider with time, expanding under the influence of gravity and the subtle pull of dark energy. We came to understand that emptiness is not passive. It sculpts the universe with graceful patience. In cosmic voids, matter thins until only a few lonely atoms remain in spaces so large that they dwarf imagination. Surrounding these voids are the filaments, luminous threads where galaxies gather, but even these glowing structures occupy only a tiny fraction of the universe's total volume. The rest is openness, deep and soothing, stretching farther than any human mind can fully grasp. Dark energy, the invisible force accelerating the universe's expansion, ensures that this emptiness will grow even more dominant as time marches on. Galaxies drift apart, the cosmic web stretches thinner, and the spaces between structures swell into vast, lonely seas. The future universe will be a place where islands of matter drift in near endless darkness, each galaxy isolated from every other, each star cluster alone in an expanding ocean of stillness. In the end, the story of the universe is the story of emptiness embracing creation. It is a reminder that silence does not diminish beauty, it enhances it. Emptiness is not merely the absence of matter, it is the gentle canvas upon which the cosmos has painted its grandest masterpieces. And as we settle back into our own quiet moments here on Earth, under a sky glowing with distant starlight, we are reminded that even in the vastness of space, emptiness is not loneliness. It is spaciousness, openness, and the quiet breath of a universe that has been expanding into serenity for nearly 14 billion years.